Welcome to this video on heat capacity applications. So I want to go through an example we saw earlier where we've got a kilogram of water and a kilogram of iron. And we saw that in order to increase the temperature of each of these by 1 degree Celsius, we need a different amount of energy. Water takes 4,180 joules to increase the temperature of a kilogram of it by 1 degree Celsius. When you look at iron, it only takes 450 joules of energy to do the same thing. Why? Again, this is the heat capacity. So the heat capacity of water is, so C water, 4,180 joules for every kilogram degree Celsius. And when you look at iron, the heat capacity of iron, it's only 450 joules per kilogram degrees Celsius. So much lower specific heat capacity. Now, what does this mean in practical sense? Well, let's give each of these containers, and these containers represent the heat capacity, a certain amount of energy. So let's give each of them 450 joules of energy. Now remember, these are containers that are representing the heat capacity of iron and water. So if we add the 450 joules in here, very quickly, the temperature is going to go up by 1 degree Celsius. Now, if I add the same amount of energy over here, 450 joules, it barely makes a difference. It takes a lot more to fill up this container. A lot more energy is required to increase the temperature. So here, my temperature might only go up by 0.1 degrees Celsius. So you can see how very quickly we can add energy and increase the temperature of the iron, where we need much more energy to increase the temperature of the water. And we looked at why water is so unusual. So we saw that basically we've got uneven electrical charges on the water molecule as a result of polar covalent bonds between oxygen and hydrogen. This results in positive and negative ends, and the interaction of these charges causes quite strong attractive forces. And therefore, it's quite hard to make these molecules move. So if you want to increase the temperature, the EK, and move these particles, it's hard. They're locked in place pretty well with these strong attractive forces. So to overcome the forces requires lots of energy, and hence the large heat capacity of water. There you go. Now, let's look at some practical examples. So here's the question. Which one here heats up faster, the sand or water? And all of you have been at the beach at some point in your life, and you saw that very quickly the sand is incredibly hot. It's a high temperature, yet the water stays cool. Well, when you look at the heat capacity, remember the heat capacity of water is very high. So it takes a lot of energy to heat up the water. So even though the sun is giving the same amount of energy to the water and to the sand, the water's temperature barely changes versus the sand, which changes significantly. Again, the sand would be the smaller container, analogous to the smaller container. The water would be this larger container, so it takes a lot more energy to heat up the water here. So that's why we have this. Well, let's look at another situation now. Well, what happens at night? Let me just copy these. So at night, which cools faster, sand or water? Well, which one cools faster? Let's check it out. Again, we'll use this analogy over here with our two containers. Bring them down here. Now, remember, these containers were quite full. So these were filled up during the day. This represents the energy in the sand that it absorbed throughout the day. This would be the energy absorbed by the water throughout the day. So you can see here, the water absorbed a significantly greater amount of energy. Now, what would happen if we empty some of this energy out? Well, you take some of the energy out, you can see how quickly the temperature change would occur in the sand. So the sand loses the temperature and its energy very quickly. Water barely makes a difference. So the water appears to stay warmer and be warmer at night. And in fact, it is, because it's going to take so much longer for it to lose all of that thermal energy it was absorbing throughout the day. There you go, heat capacity of water. How about this? What about a sea breeze? Well, a sea breeze is very simple. What happens is, again, during the day, you have to remember this, the land heats up much, much, much faster, lower heat capacity, so it's going to be having a higher temperature. It's warmer. Because it's warmer, the air is going to rise because of convection, and it's going to go over and begin sinking over the much cooler water, and it forms a little convection current. And if you're on the beach over here, you're going to feel a nice cool breeze coming in off of the water. That's called a sea breeze. If you want, call it a lake breeze if you're on a lake. Now, what happens at night? Now, remember, at night, the land, because of its low heat capacity, cools off much, much faster than the water. Because it's cool, the air is going to be sinking there. And as a result, it's going to go over to the water, which is much warmer at night, because remember, it hasn't had a chance to cool off, because it still has lots of energy. It's absorbed. The air rises there and gradually comes down. So this would be called a land breeze. So at night, we tend to feel much, much cooler at the beachfront as a result. This is not as strong as a sea breeze, but nonetheless, we do have this reversal. And the neat thing is, think about it, early in the morning and at night, just not too late, during the transition from sea breeze to land breeze, the lake is nice and still. You'll notice that. So that's why we have nice still lakes. There's a nice transition because the temperature is about even on the land and in the water at those points of time. All right, how about this one? Which one stays warmer longer? Well, of course, the water bottle. Why? Because remember, it actually has water inside of it. And because water has a high heat capacity, remember, it takes forever and ever for it to heat up, but also takes forever and ever for it to lose all that thermal energy. Versus the metal, which very quickly increases its temperature and very quickly decreases its temperature. So which one do you want to use to stay warmer, longer? Of course, the hot water bottle. Same thing's true in baked goods. So here's a nice piece of pie. Remember, inside the pie, you've got a nice juicy filling full of water. So guess what stays warmer longer? The filling. And that's why you've got to be careful. When you've got the filling, it has lots of water. It stays warmer much, much longer because it has to take a long time to release that energy than the crust. The crust is hardly any water. You can touch the crust as soon as it comes out of the oven. You won't get burned. Yet the water is going to be very, very hot. Plus the fact it's inside, it's insulated. That's besides the point. So again, that's why, heat capacity. How about this? We are made up of a lot of water, 70% of our body. So 70% of our body is water. It's hard to change the temperature. So it's very hard to lose all that energy, but it's also very hard to get that energy back. So water tends to moderate our body temperature, allows it to stay at a relatively constant level. This is really important for organisms such as lizards that are cold-blooded, and basically they don't have a way of regulating their temperatures. They're really dependent on water. Metal pots. Why do we use metal pots? Fantastic conductors, but remember, low heat capacity. They heat up in a jiffy, really, really, really fast. Water, why does it cool so well? Again, high heat capacity. You remember we did the demo with the conduction of the different metals? We had that spoke-like device, look like this, and we had paper clips at the end. It got really, really hot, and when it got really, really hot, remember, what we did is we put this in water, and the water very quickly absorbed all of the energy from the spoke, and the spoke cooled off very, very quickly. So it's great. It has a high heat capacity, lots of opportunity to absorb energy. Remember, it's like a container. Lots of room in this container to absorb energy. Okay, seasons. Why are they delayed near the water? Well, let's check it out. If I'm at point A, say it's I don't know, spring, like right now, spring. Remember, the land has been very, very, very cold for a long period of time. Now, as the sun rays come down at point A on the land heats up very quickly because it has a low heat capacity. So we'll feel warmer here. So you're very warm here. This will be in the spring. Now, Now, here at B, we're surrounded by lots of water in Mississauga. So the water, remember, it's been cooling off all winter. Very, very low energy. So it takes a lot of energy to heat up all of this water. So if you go to the lake right now, it's freezing. It's going to take a long, long, long time for it to warm up because of the high heat capacity of water. So as a result, areas near the lakes right now are going to be much, much, much cooler for a long period of time. Now, what happens in the fall? It's the opposite. The fall and into the winter, the areas near the lake are going to be warmer because the water has absorbed all that energy throughout the summer and it gradually releases it as a result. So it's really the opposite. So we have a nice moderating effect because of the Great Lakes around us. Burning yourself on pizza. Well, crust, low water, sauce, high water. You figure that one out. Burn yourself on soup, but not on toast. Water, no water. Again, you get the idea. So fundamentally, make sure they can explain all of these applications of heat capacity related to the water content, really. The more water you have, the longer it takes to heat up, and the longer it takes for it to cool off. And that's it. So hopefully you enjoyed the video on applications of heat capacity.